Okay, so last time we were talking about spherical coordinates, and let me just remind you, here they are, theta, phi, right, and then rho, that distance. And we talked about last time about how to relate them to rectangular coordinates. The big idea is to remember that based on looking at this triangle, r is rho sine phi. Once you make that realization, you're 2/3 of the way there. X is r cosine theta, y is r sine theta. We already knew that, right? So that's easy. And then based on looking at the same triangle, not hard to see, z is rho cosine phi. Okay. Then go in the other direction, sort of. We have that for rectangular coordinates, and this for connecting spherical and cylindrical coordinates, in case that might be useful at some point. Okay. All right. So, yeah, again, just like with polar coordinates, they're not unique. Spherical coordinates, any given point has lots of spherical coordinates. Infinitely many, in fact. Okay, so ignoring the whole plus 2 pi n thing, which always works, right? So let's just go ahead and agree that, yes, you can always add 2 pi to any angle. Right? They're still not unique, right? Even though with polar coordinates, they were kind of what I'm going to loosely call two sets of polar coordinates, right? One where rho is positive, the other where rho is negative, right? Well, there's 4 with spherical coordinates, and it's just some sort of geometric gymnastics to make the realization as to how that works, right? And here's an example. So let's consider this point here, right? So we've got those rectangular coordinates, right? You can plot that point. Here it is. And let's talk about the different ways that we could represent that point in spherical coordinates. Now, it's not hard to do the little bit of geometry, and you can persuade yourself that this angle here is pi over 6, right? And you can persuade yourself that that angle there is pi over 4. It's just a matter of looking at these numbers and drawing the picture and thinking about the appropriate triangle and remembering all your trig. Okay. And this distance, 2 square root of 2. All right, so that being said, one sort of free way, the obvious, the most natural, the easiest way to recognize this point in spherical coordinates is to think about this half plane hinged on the z-axis there. Think of that as theta equals pi over 6. That's that plane, theta equals pi over 6. Now, from the vertical, then, and in that theta plane, how far do you have to go down that way, in the direction of the theta that's been chosen, to get to the direction that the point is? Well, that's pi over 4. And then, now that we've defined the direction, what's the distance that you go in that direction? Well, 2 root 2. Okay, so that's the free one. That's the easy one. Right now, let's think about different, possibly weird ways that we could get to this same point by way of different spherical coordinates, and importantly different. Again, we know that it's kind of a freebie. You can add 2 pi to any angle, right? So we're noting those, but it's not worth dwelling on them. Okay, so here's hopefully a familiar flashback. The polar coordinates, this half plane, right, that comes from thinking about that angle, pi over 6, but what if you just went around an extra half turn? Going around an extra half turn, you would get that half plane kind of back there, if you will. That angle is an extra an extra half turn. That's an extra pi. So that's 7 pi over 6. Yeah, everybody on board with that? We did that kind of thing with polar coordinates. Now, okay, from the vertical and in the direction of that selected theta, now how far do you have to go sort of that way to get to that direction? Well, you kind of got to go backwards, right? So I'm going to call that negative pi over 4. Positive pi over 4 would be over there, and that's not where we're going. Is everybody on board? Okay. Okay. And then again, in that direction, how far do you go? Well, it's again that distance, which is 2 root 2, just like before. Okay. All right. So that's two different options. Now, are those the only two? Well, no. There's another two of them, and these get increasingly sort of unnatural seeming. Why would someone choose to do that? And most of the time we're not, but I think this is a good exercise in just thinking through the geometry of spherical coordinates. So let's talk these through as well. We're going to go back to thinking of theta as being pi over 6. So we're back in that half plane there. And now let's think about what if we were to choose this weird choice of phi. Let's not go pi over 4. From here, let's not go pi over 4 in the direction of that theta half plane. Let's go backwards, negatively, in that kind of same general direction, but backwards, and then by 3 pi over 4. And, well, that gets us to that direction. And then in that direction, we go backwards by a distance of 2 root 2, thus the negative, and that gets us to the same point. Right now, again, it's pretty contorted and weird to think about doing that, but you got to give me that would work. I mean, that does give you the same value of x, y, and z using the formulas above. Okay, all right, so weird. And then let's see, last option. Back to 7 pi over 6. Now that was already weird enough. Whoops. Sorry, let me try to do 7 pi over 6 is already a weird enough of a choice. And now we're going to do 3 pi over 4 in that direction. So rather than saying, well, there's vertical and there's where I want to go, so let's go backwards by negative pi over 4 like I did there, instead, we're going to say, well, let's go positively. Now, I need to get to here, which means I've got to go all the way around down to that direction. And that gives me a direction which, if I go negatively, gives me the point in question. Yeah?
So how'd you go from the original order triplet to any of the information?
So that's just trigonometry, geometry, trigonometry. So let's see here. Oh gosh, did I make a geometry error here? Y is, I think I have this yeah, I'm sorry, look at that. That's a 1. So it looks like I made a change of my mind as I was making this example, and I forgot to change it up there. Good catch again. Yeah. So that needs to be a 1. That makes this a 2, 1, square root of 3, familiar 30, 60, 90 triangle, right? And that being 2 and this being 2 makes this a familiar 45 triangle. Yeah, right. Thank you. Okay. Can I remember that one? Okay, and so at that point, it's good, right? Okay. Anybody else? Here's the good news. Most of the time, we're going to be doing stuff like this. Okay. All right. So moving along. Now, I'm going to be quick with this page here. This is not in the book, and this is just this is kind of a cute observation, but these angles, theta and phi, defined on the previous page, they kind of not that terribly different from longitude and latitude on the surface of the Earth, if you think about it, right? In fact, if you were to draw your Earth like this, right, and if you were to make this the Greenwich line, right, and let's see here. Well, then, with that setup, notice theta is just east longitude. So the spherical theta is the geographic East longitude. So how about that? Now, phi is not exactly latitude, but it's not the most different thing in the world. Phi is measured that way from the North Pole. North latitude is measured this way from the equator, and notice that they add up to pi over 2. So, not the same, but really, really closely related. Punchline, if you know longitude and latitude, and if you know that you're on the surface of the Earth, which we are most of the time, right? Then you know rho, phi, and theta. You know spherical coordinates for where you are in space with this axis system. Right? So, having observed that, the big idea is longitude and latitude tells you spherical coordinates. Spherical coordinates tell you x, y, and z. So we have a pretty easy process for figuring out where x, y, and z you are in space when you're on planet Earth. Right? Okay, who cares? So here's a reason why you might care. So let's consider the following question. Let's suppose we're somewhere on the surface of the Earth here, and let's see. So I'm here, and I want to get to there. What's the fastest way to get there? Right? Well, there's a temptation to look at a map and say, well, the shortest distance between 2 points is a straight line. Just draw the straight line and drive that way, right? Or fly that way, right? But there is no actual straight line. This is curved. So there is no such thing as a straight line. Okay, but yeah, the map is flat, and you can talk about straight lines on a map. Which map? There's lots of different kinds of maps. There's lots of different ways to take a curved surface like a sphere and turn that into a flat thing that we call a map. And they are very geometrically different. The most common one, the Mercator projection, is severely contorted. All maps are severely contorted. But the Mercator projection in particular is severely contorted, right? And so you see ridiculous stuff on the Mercator projection, like, let's see here, let me draw. So here's, gosh, this is going to be bad, sorry. Here's North America, right? And then Greenland is this monstrous thing, right? It's not that big, right? It only looks big because this teensy-tiny little circle up here near the North Pole gets stretched out to be just as long as an equator near the origin, right? So that's pretty bad, right? That's pretty contorted. Okay, so this kind of map is inaccurate. And so if you just say, well, I want to go from this purple point to that purple point, wherever that is, just by a straight line, no, that's probably taking a path that's unnecessarily bent toward the equator. It's not going to be the shortest distance. Well, this seems like a hard problem, right? How are we going to find the actual shortest distance, between that point and that point? What is the sort of the correct path? What is the optimal sort of way of doing it? And if you restrict your thinking to the map, it is a hard problem. And most people do. Most people restrict their thinking to, well, here, this is how we view the Earth. We look at maps. So on that map, how would we find the curve that takes sort of maximal advantage of the sort of the shrinking of horizontal distances near the North Pole, right? Seems like a hard problem. Okay, here's how it's an easy problem. Don't think of it on a map, for crying out loud. What a ridiculous way to think about a geometry problem on a sphere by trying to imagine it on some totally distorted representation of that sphere. Here's the easy way to answer the question. That distance is what you get by looking at these two vectors and just look at the angle between those two vectors. What could be easier than that? Right? That's the shortest distance. Right? So the reason that we want to view these points, let me get rid of all this distraction here. The reason we want to view these points as rectangular coordinates, right? So why do we want to do this? Is because viewing those points in rectangular coordinates allows me to understand their position vectors once I understand their position vectors, I can understand this angle, right, by way of a dot product. The dot product being very easy to compute in rectangular coordinates. And once you know that angle, then you can compute the actual distance that we're interested in by an old high school geometry formula. The length of an arc is the radius times the angle. So, don't think about it that way. That's much harder. Okay, anyway, neat observation. If you want to know what's the distance, the actual distance on the Earth, as the plane flies, between, two relatively northern, if you're on the equator, it's easy, just stay on the equator, right? But the further you get up away from the equator, the closer you get to the poles, if you want to fly from, New York to Moscow, right? The effects are very significant there, and this, connection to spherical coordinates crushes that problem very nicely. Yeah, cute. Okay. Just like with polar coordinates, there's questions about how to convert between one coordinate system and another. Here is a sphere in rectangular coordinates. Now, this is a sphere centered at, 1, 0, 0, as you can see in the algebra right there. So, how would you write the spherical equation for this sphere? I want to write this, the equation for this surface in spherical coordinates. The good news is the process is very straightforward. Where's my little button? There it is. Process is very straightforward. So first of all, multiply everything out, right? So this is x squared minus 2x plus 1. So crank that out. And then just start plugging in known relations between the various coordinates. So for example, I already know this. So let's capitalize on that, put that in there. We know that x is rho sine phi cosine theta from 2 pages back. Right? Standard formula. The ones cancel. Right? And now it's I'll cancel a row, move something to the other side of the equation. There you go. It's a spherical equation for that sphere. Straightforward process. Okay. Let me take a pause. Any questions before I go on? The integrals. Okay. Right. Okay. So, y'all recall that I made a decision to do the topics in a different order, right? So integrals and polar coordinates in the book comes right after double integrals, which is fine. This is a perfectly respectable way to do it. I think there's a big advantage to doing it the way that I've done it. Now, recall what I've done is I did not do polar coordinates then. We went ahead and did double integrals and then triple integrals. And then, very quickly, I did change of variables all the way back to section 14.9. So why do change of variables, section 14.9, before section 14.4, integrals and polar coordinates? And the answer is because you can think of this as an example of change of variables, as it turns out. So in fact, it almost leaps off the page as you think about it. These formulas give x and y as functions of two other variables, r and theta. We're accustomed to them being like u and v, but whatever, right? Two output variables as functions of two input variables, and you can just choose to think of that as a change of variables function. Right? It's just as good as any other change of variables function we might write down. It turns out this is a fantastic change of variables function. We're going to see some examples. Now, we know that if we're going to use change of variables, then this function, we're going to have to find a formula for the stretching factor, right? That's always the first thing you got to do. If we're going to be using this specific change of variables function a bunch, how about we do this calculation one time and remember it, so we don't have to crank out this calculation every single time. So here's how that calculation goes. It's just a matter of writing it down, but the partials are, missed. The partials are like so. The determinant, usual rules, multiply those out and get some nice Pythagorean cancellation. That's cool. How convenient. And here's your answer. Your stretching factor is just the absolute value of r. And that further simplifies if you make the choice that I urge you to make, if you choose to only do polar coordinates with r being positive, then you can lose the absolute values, right? And your stretching factor is just r. So this is an odd little bargain that we make here. We choose to constrain ourselves when we're doing polar coordinates. If we're going to view this as change variables, function, stretching factor, all that business, we're going to constrain ourselves and only allow ourselves to do what we wanted to do anyway. Nobody likes using negative values of r. It's weird. It's unnatural seeming, right? So, like I say, it's an odd bargain. It's a win-win bargain. If we choose to restrict our attention to that which is most convenient, then we get this very convenient benefit that we can lose the absolute values. So it's, almost always. I mean, if I go to great trouble, I can come up with maybe an example where you might not want to make that choice sometimes. But it's weird and unnatural and rare. So as far as Math 212 is concerned, we're always going to make this choice. When you're doing polar coordinate integrals, always choose r to be positive. Your stretching factor then is just r. Okay. So, good news. Let me take a pause before we go on. Anybody have any questions about that? So we know our stretching factor. Now we can just start doing pullbacks. For example, let's just say that our domain looked like this, right? You can imagine doing a double integral over that region, and as you slice, you're going to slice through corners. So this is 3 separate integrals. Yeah. Not only is this 3 separate integrals, some of those bounding curves are circles, which means when you solve for one variable in terms of another, you're going to have square roots. So this is 3 undesirable integrals, not just 3 integrals. Right? Okay. Not hard to persuade yourself, though, that the pullbacks, right, this line, theta equals theta 2, well, that becomes that line. And let's see here, likewise, this line becomes that line. And this curve, well, that's where r is a fixed constant value, r1, so that becomes that. And this curve there becomes that. The pullback domain is a rectangle. Everybody happy with that? Okay. All right. Okay. So rather than do an integral there, we're instead going to do an integral over here. The way I've presented this so far, we've drawn 2 pictures. We've drawn a picture of our original domain, and then we've drawn a picture of our new pullback domain. We know our stretching factor. And from looking at the pullback domain, here it is, we can figure out the bounds on the resulting integral. So this is pretty straightforward. Maybe we have r go from r1 to r2, and then for some given value of r, theta goes from theta 1 to theta 2, right? And we get to that by, as we always have, looking at the actual process of slicing up the pullback domain. Okay, so here's the big idea. One of the big ideas of polar coordinate integrals. You don't have to do that. Any slice that you take over here, for example, let's talk about this. Here, let me do this one. There is a slice. That's a theta slice. We're fixing some value of theta. And I can see that theta slice in my r theta plane, but clever observation, I can see it over here in the xy plane if I could draw where the darn. I can see it there too. That's that same theta slice just drawn in the xy plane. So if I want to, look and say, what's the range of values of theta on this new pullback domain, I don't have to draw the domain and then actually go through this slicing process over there. I can say phooey on that whole thing. I can just come over here and say, well, here's what if I were to draw the pullback domain, and I don't want to draw it, but here's my first theta slice, and those theta slices look like this. Well, at least they do in the XY plane, and the last one is there. So even though we're doing a change of variables, there is a pullback domain. We don't actually need to draw or even really think very much about that pullback domain. So we just saved ourselves a bunch of drawing challenges, right? So that's nice. So in this same direction, now we know the range of values of theta. Now let's fix a theta and ask what's the range of values of r. Well, r starts there and ends here. All of that makes sense over here as well. There's an arbitrary theta slice, and for that value of theta, that point tells me my starting value of r. That point is on that, what you might call r slice, which has that value of r there. And the ending value corresponds to that point, which is on that r slice, R2. Yeah? So the whole slicing process can be done entirely over here, entirely ignoring all of that. Okay, so ultimately you are doing a change of variables. You've got to recognize that you're doing a change of variables because you've got to understand that you've got to put a stretching factor in there. That's absolutely non-negotiable, right? But even though you are doing a pullback, that doesn't mean you have to draw the pullback. Just figure out everything you need to know about your bounds from that picture. Here's another quick example. I'm going to leave it as an exercise for y'all to confirm that r equals sine theta is a circle in the xy plane. And we can go through the theta slicing process. Oh, of course, we can also plot r equals sine theta. I mean, there's r equals sine theta. Right? But that whole slicing process, you can see that in the xy plane. So, you might say, well, theta goes from 0 to pi. So there's kind of my first, these are my various theta slices. Right? It's real easy to see. That's where theta is equal to 0. This is where theta is equal to pi. Right? Then for a some given value of theta, let's just pick one. Let's say that value of theta. The starting value of r, well, I would have drawn that. I would have drawn that over here, where I can see r is 0, but I can also very comfortably see there r is 0. I'm at the origin. Of course, r is 0. Right? It ends, I could have done it by saying, well, it's at that point's on this curve, that curve has this equation. But I can also just as well do it and say, well, the end corresponds to that point is on this curve. Yeah, sure, I'm viewing it in the xy plane, so what? There's the equation, same equation. Okay, all right, let's get our hands a little dirtier. Do an actual example. Here we're looking at an integral on this domain here. Of course we could do that in rectangular coordinates. Sure, right? But let's not. Let's see if it might be easier to do this in polar coordinates. So let's see here. We got to think about what's the range of values as you slice it up. Now here's what the pullback domain looks up, but again, we don't need that. So let's kind of generally sort of not look at that. What is our range of values of theta? Well, there's my first theta slice. And if you insist, then sure, there's that first theta slice. Here are various theta slices as you go along. If you want to view it in the r theta plane, you can. There it is. Here's our last theta slice. There. Right? Now, I suppose you could have asked yourself, okay, this line, what's the equation of that corresponding line, and then what's the value of theta here? Or, as I think is much easier, just, using your existing intuition of polar coordinates in the xy plane, just see that's theta pi over 2, because that's where pi over 2 is. I don't know, that's just standard polar coordinates observation. Okay. Okay, so in doing this pullback, theta 0 to pi over 2. Now, for a given theta slice, what's the range of values of r? Well, r starts there at 0. R ends there at, okay, wait a second. What is that point? That point is on this curve. That curve is part of the boundary of the unit disk, so that's where r equals 1. So r goes from 0 to 1. Okay. So, didn't need this picture at all. Right? This domain gives us those polar bounds. Don't forget to do the pullback of the variables. The big warning, of course, don't forget your stretching factor. You don't just symbolically replace dx dy with dr d theta, right? Those aren't the same thing, right? The stretching factor's got to go in there. It's so easy to forget the stretching factor. I cannot emphasize enough. So many people forget that stretching factor. Make sure to put that in there. There you go. Now, yeah, question.
Do we have to show how we get the stretching factor for polar? Or
No, you can just cite that. If you want to use do a polar coordinate integral, just write down dx dy equals r d theta, just like I did here, and no justification required. It's very, very standard. Yep, great question. Anybody else? Yeah, okay. By the way, also, you've got to simplify your integrand there I'll come back to that in a minute. Okay. Let's see here. Here is another example. Suppose your domain is this entire disk. What's the slicing process there? There is this temptation to say that as theta increases, it just never stops. Theta just keeps going around and around. I never get to the end, right? But the point is, if you were to draw, if you were to do the pullback, you only need to go far enough until your slices make it all the way around once, and then you've covered the whole domain. Not only is there not any need to go any further, if you go further up here, then you're double counting in the XY plane, right? So this is just, I like to throw this example in there. If you go all the way around just means 0 to 2 pi. Okay. A couple of bits of good news. It's very rare that you need to make a real choice as to which way to do your differentials. When you're doing polar coordinates, technically you could do d theta dr instead of dr d theta. It's extremely rare that that's a good choice. It's just hardly even worth talking about, right? So just go ahead and always do dr d theta, at which point notice that you can just memorize this particular expression, r dr d theta. That's what dx dy is. That's what represents area in the xy plane. Sometimes written as dA, right? So r dr d theta. Think of that as kind of like a single thing. My little personal, memory tool, life hack, whatever you want to call it, for not forgetting to put the r in here is that when I write down my differentials for my polar coordinates, I always write the whole thing down at once. So I don't ever, let me rephrase that. I try to never just write down that, right? Always write down r dr d theta all at once. After all, you are replacing dx dy. Dx dy is not equal to dr d theta. Dr d theta by itself is not really a thing, right? It's got nothing to do with an integral in the xy plane thought of by itself. So just don't ever write it down on its own, right? Always write down r dr d theta. Now this gets me back to the other thing I was going to say earlier. Yes, while it is true that you should think of this as kind of a single thing, once you've gotten your integral written down, don't forget this is, in fact, part of your integrand, right? So I've seen some students that will overinterpret. Take me a little too seriously on saying, think of this as a single thing, and infer that somehow this is part of the differential and it doesn't participate, and that, in the anti-differentiation. And just, make sure you understand, no, it's a stretching factor. Of course it's part of the integrand. So you do have to combine it with the integrand once you've got your, integral all written down. Okay. Just think of it as part of this single thing as you're writing that integral in the first place. Okay, and I just got several more examples here. I'm going to go through these examples maybe a little quickly because there's a bunch of them, right? And we've already done several already. Okay, so let's suppose you want to do an integral over this annulus. Washer, maybe you prefer. And I want to do an integral of this integrand, 1 over the square root of x squared plus y squared. So how would you do that integral? Now there's two different. Well, there's one thing you could attempt. You might try to say, well, how about I'll do the integral over the big disk, and then I will subtract the integral over the small disk. And, well, shouldn't green minus blue give me the annulus, right? And here's the problem. Over either of those disks, if you do an integral over that disk there, the integral is undefined. Right? If you think about it, it has to be undefined. This integrand here is not defined at the origin. Right? X and y are both 0. Integrand's not even continuous. What's an integrand of a function? What's an integral of a function that's not continuous on the domain? We don't even have a definition of that. It's a big problem. Right? So you can't do that. Okay, fine. So so here's the next thing you could try. You could say, well, let's just okay, fine. We'll restrict our focus to the annulus. And now we'll start slicing. And, of course, you can see this coming. The slicing process gives you 4 separate regions that you'd have to do. A separate integral, so we have 4 integrals, all undesirable because there's just square roots everywhere, right? All of our bounds are circles, and so square roots everywhere. This is a terrible, terrible way to approach this problem, right? Okay, so let's instead use polar coordinates, and it's just no big deal. Let's see. Well, I guess I'll do this in purple. It's fine. So theta. Start there at theta equals 0. End there at theta equals 2 pi. Right? For any given value of theta, let's say this one. R starts at that point, which is on that curve, which has that equation, and therefore start with r equal to 1. We end at that point, which is on this curve, which has that equation, and thus we end at r equals 2. And it turns into this perfectly innocent polar coordinate integral. Don't forget your stretching factor. I make a big deal about the don't forget your stretching factor because I have to just point out, it happens so often that students are spending so much time thinking about the domain and how to slice and which way does what's the range of values, and then they're so focused on the domain they in fact very often forget. And it has helped for me to make a big deal out of it in class. Don't forget the stretching factor. Oh my gosh, it's a big deal. It helped, but it still happens. Right? So make sure that's not you. Right? Make sure that you don't ever replace dx dy without including the r as r dr d theta. Okay. All right. Here's another sort of weird example. Let's see here, let me zoom in a little bit. So the curve that makes up what we're talking about here, this curve goes like that, and that's a spiral that comes from this equation, r equals theta. Yeah, it's kind of neat. And it keeps spiraling out, bigger and bigger. So with that spiral, notice that you can define a region here. Right, and how would you compute the area of that region? There's two weird things about that region. On the one hand, that is a weird curve. And on the other hand, it's got this little divot taken out of it over here by that part of the same curve. Okay, all right. So how are we going to do this? Well, it's no big deal in polar coordinates. You have to be a little bit careful. Theta starts at 0. Theta ends at pi over 2, no big. Right? Now, for a given value of theta, let's pick some value of theta. What's the range of values of r? Here's where it gets confusing. What a lot of students want to do, and I see the temptation. A lot of students want to say, well, this point is on this curve. This point is on that curve. And let's see, the ending point is that point, and that point, it's on the same curve. And so there's a temptation to have the integral go from theta to theta, which of course doesn't make any sense. All right, so what's happened here? Okay, when we first wrote down r equals theta, we weren't putting any restrictions on what theta could be. And so in fact, as we made our way around, the values of theta over here, they are a full turn larger than the values of theta over here. Now, then, as soon as we restrict our attention and say theta now between 0 and pi over 2, well, if theta is constrained to be within theta and within 0 and pi over 2, this is no longer r equals theta. This curve here is now r equals theta plus 2 pi. Right? It would have been r equals theta had we let theta go around an extra full turn, but we didn't. Right? So that's r equals theta plus 2 pi. This little thing here is r equals theta. So for a given value of theta, we go from the blue curve to the green curve, and the integral then r goes from theta to theta plus 2 pi. So anyway, a little tricky, a little weird example. Okay, so how do you know when you should use polar coordinates? This is another tool for your toolbox type situation. I can't tell you it's exactly going to be used. Whenever this happens, you have to use polar coordinates or anything like that. It's useful sometimes. Now, so the tip-offs, or the earmarks that I can give you for when polar coordinates is likely to be useful. Think about maybe the domain might be easier to describe. Circles tend to be a real, red flag situation, because circles are really awkward to describe in rectangular coordinates. Right? You got to solve for the one variable in terms of the other, and you get square roots. You get square roots in your inner bounds, which means you have square roots in your integrand for your outer integral. Hard integrals, bad. Right? So circles tend to be easier. Be on the lookout for circles in your domain. Sometimes the integrand might be a little bit easier to differentiate. So x squared plus y squared, not that it's that bad, right? But that's one less term. It's r squared in polar coordinates. Even more so, square root of x squared plus y squared in rectangular coordinates is r. Much easier expression in polar coordinates. Okay, so be on the lookout for this kind of thing. Just another example here. Let's suppose that our domain, this would be a nightmare in rectangular coordinates. This crescent moon kind of situation here, right? So how would we, if that were our domain, how would we do this in rectangular coordinates? Okay, all sorts of problems, right? It's going to be 3 separate regions no matter how you slice pass. In polar coordinates, this is what your slices look like from a starting point to an ending point. How do we know where those ending points are? Well, we just got to do the appropriate algebra, figure out where, for example, where is that point. A couple different ways that you can do that, but once you know where that point is, then you can find the value of theta. Let me show you my favorite way to identify where that point is, and that is, while you could write down the actual equations of these curves and see where they intersect, it's easier to just say, well, look, that distance is 1 because it's part of that circle. This distance is 1 because it too is part of that exact same circle. And then finally, this distance is 1 because it's part of that circle. So that's an equilateral triangle, and we know therefore that that angle is pi over 3. So clever. Right. This kind of thing comes up sometimes. We'll be on the lookout for that. Yeah. Okay. Again, don't forget your stretching factor. Yeah? Okay. Everybody good? Okay. This next example. This is a classic calculation. This was first done a couple hundred years ago, and it's just really cool how this works out. It's an example of an idea that happens in math sometimes. Sometimes if you have a hard question, make it harder, and that helps. It really does sometimes. So here's the question we want to consider. If I wanted to evaluate this integral from negative infinity to infinity, e to the negative x squared dx, how would I evaluate that integral? Some of y'all may recognize this integral from Calc 2, right? In Calc 2, they talk about statistics and probability a little bit. This is this curve is a normal PDF. Do y'all remember normal PDFs? Okay, Gaussians they call them sometimes. Well, we need to compute integrals of normal PDFs to compute probabilities. That's what PDFs are, right? So this is a very natural integral to want to be able to compute. Bad news, it is impossible, and I don't mean that in the casual colloquial sense. I mean it is actually impossible to find an antiderivative for that function. Without using Taylor series. And so now, of course, if you do, yes, you can write it down with Taylor series. You can do the antiderivative with Taylor series. And now you've got to compute an infinite series. That's another thing that we can't do. Right? So that's not a good way to approach the question. So how do we evaluate this integral? Hard problem. Let's make it harder. Let's multiply it by itself. Let's not just compute this hard number. Let's compute the square of this hard number. Super clever idea, as it turns out. Here's why. There's this number j times itself. See, that's j. And this is also j. Now, the point is it's the same underlying integral. We're using a different dummy variable. We're using y instead of x, but it's just a dummy variable. It's just something that represents the values that range over, as indicated. So, doesn't really matter if I rewrite j like that. So this expression involving two different variables is really just j times j. Yeah? Okay. All right. Now, next step. This has x's in it, so it looks like this is an expression or something, function of x, but it's not. X is a dummy variable. This is a number. It's a constant. It's called j. Right? So being as it is a constant, being as it is completely independent of y, it's just a value. I'm going to move that inside of this integral, weird though it seems to do that. Right? There it is. Here, let me do that with that here. There it is. Why I'd want to do that, not clear, but free country. I want to do this. You have to let me. Right? Okay. Now, similar argument. This y is a constant as far as the x integral is concerned. And I'm going to pull this now inside of the x integral. Like so. All right? Everybody on board? Okay, so I took a hard problem, I made it harder, and now I've made it weirder. Right? Okay, so not clear where I'm going with this. Okay, here's where I'm going with this. And I wish I was clever enough to have this insight on my own. Somebody showed this to me, but a little bit of algebra there. Notice that now we have an integral as x and y range over all different values. This is actually now a double integral. We've moved on now from a single variable calculus question to a multivariable calculus question, right? Again, we took a hard problem, we made it harder. But it's not just harder. It is now in a context where we have other tools. And the big other tool that we have here is I'm going to choose to do this integral instead of rectangular coordinates. I'm going to choose to do this in polar coordinates, right? So theta goes all the way around. For any given value of theta, r goes from 0 all the way to infinity. That's still R2. That's still the whole plane. X squared plus y squared is r squared. And it's basically all over but the shouting at this point. I mean, again, it's weird how sometimes you take a hard problem, you make it harder, and then it unravels and turns into trivialities. This is an easy integral. The thing that makes it easy, of course, is that this stretching factor from polar coordinates is exactly what we need to be able to do a u substitution now. Isn't that super clever? I never would have thought of this myself in a million years, right? But really clever idea, and it all unravels. So now you got to write this, of course, as an improper integral with a limit. So, fine. Y'all remember all of that business. But you crank it out, and there's that integral. Now, it is easy to inadvertently spike the football on the 2-yard line here. Let's not make that mistake. We just computed j squared, right? So what we actually wanted was j. So don't forget to take the square root. Everybody happy? Classical calculation. Okay. Oh, and I'm sorry, I'm out of time. Okay, all right, we'll pick up there next time. Oh, let's see here. By the way, today is Wednesday, and conveniently, we did just finish integrals in polar coordinates. We have not yet done cylindrical and spherical coordinates. So I owe you all an email, but the homework will include this polar coordinate integrals business. I'll send an email later. See you later.